Welcome to Submodule 2 of 3 of our training on extended reach drilling. In this module, we'll strengthen your understanding of ERD by building on the fundamentals covered in Submodule 1. First, we'll revisit the definition of ERD wells, reinforcing how extended displacement ratios set them apart from conventional wells. We'll then examine equivalent circulating density management. ERD wells face unique ECD challenges due to shallow vertical depth and long lateral sections, making fluid pressure control far more complex. Next, we'll address trajectory design. Unlike conventional profiles, ERD trajectories must account for torque, drag, hole cleaning, and geological hazards. We'll see why a systems-based, bottom-up approach to path design is essential. Surveying and geological uncertainty is another key theme. In long-reach wells, even small positional errors can lead to missed targets or costly sidetracks. We'll also analyse torque, drag, and buckling, understanding both design forecasts and operational impacts. Finally, we'll explore BHA and drill string design, where hole cleaning capability and tool durability take precedence over rate of penetration. By the end, you'll have a clear view of the design, operational, and risk management factors that underpin successful ERD execution. Next, let's begin with ECD management. In extended reach wells, ECD management becomes one of the toughest challenges. Because these wells often have shallow, true vertical depth compared to their measured depth, circulating pressures translate into a much higher equivalent density at the casing shoe. The plot on the right shows a vertical well and a horizontal well. On the left, we have a vertical well with a measured and true vertical depth of 10,000 feet. Using a 10 ppg mud and 350 psi annular pressure loss, the ECD at casing depth is 10.7 ppg. On the right, we have an ERD well drilled to the same measured depth of 10,000 feet, but the true vertical depth is only 4,000 feet. With the same mud weight and the same pressure loss, the ECD is 11.7 ppg. So why is it higher in the ERD well? Because the same annular friction is applied over a shorter vertical column. In other words, when the TVD is shallow, that pressure loss represents a bigger percentage increase in ECD. This is because of the growth of the frictional losses in the annulus from cuttings beds and eccentric flow. This causes the ECD to climb more rapidly, resulting in a narrow mud weight window for operation. Next, we'll see how trajectory design can be optimized to help manage these pressures. Trajectory design for ERD wells cannot be reduced to simply the straightest distance between 2 points. A systems approach is needed. The well path must be designed not only for geometry, but also to minimize drilling problems. For example, choosing a shallower tangent section may reduce torque and drag, even if it increases total measured depth. Catenary profiles, curves resembling a hanging chain, have a high potential impact balancing wellbore stability with mechanical loading. These designs can reduce dogleg severity and improve casing run-in. A bottom-up approach is recommended, starting with the smallest hole size. By considering constraints such as casing wear, drag, and completion placement first, the larger hole sections can be designed to accommodate these requirements. In short, ERD well profiles must be engineered with long-term construction in mind, not just to minimize distance. On the next slide, we'll expand this discussion to highlight the key client and operational issues that must be factored into trajectory design. This slide expands on trajectory design considerations, showing the wide range of factors that must be addressed. ECD management is one. Trajectory choice influences circulating pressure, especially in long high-angle sections. Wellbore stability and potential problem zones must also guide design. If unstable formations are present, the trajectory may be adjusted to minimize their impact. Surveying and geologic uncertainty, both vertical and lateral, are more critical in ERD since small positional errors accumulate over long step-outs. Hole cleaning depends heavily on BHA geometry, choke points, and the relationship between hole inclination and hole diameter. Poor design increases the risk of cuttings beds. Casing and drill pipe wear must be considered, especially across doglegs or long tangents. Finally, the design must address torque and drag and buckling, not just for drilling, but also for running casing, liners, and completions. In some cases, it is better to drill around geologic problems rather than directly through them. This flexibility can prevent instability and reduce risk. Next, we'll turn to surveying and geological uncertainty, another factor where ERD wells differ significantly from conventional design. In ERD wells, surveying accuracy becomes far more critical than in conventional wells. Because step-outs are so long, even a small error in measured depth or inclination can translate into hundreds of feet of positional error at the reservoir. Both lateral and vertical accuracy must be managed. TVD uncertainty is especially important since being off by just a few feet can mean missing the target zone or drilling too close to a fluid contact. This requires a combination of improved practices and better technology. Options include using in-field referencing IFR, SAG corrections and dual sensor models to reduce positional error. These improvements refine both azimuth and inclination data. Any opportunity to improve understanding of the well's location should be taken, whether through higher frequency surveys, gyro tools, or surface reference corrections. In short, ERD wells demand rigorous survey planning and execution. Without it, the risk of missing objectives or encountering unexpected hazards rises significantly. Next, we'll discuss torque, drag, and buckling, mechanical factors that are critical in long-reach wells. Torque, drag, and buckling are mechanical limits that often control ERD design. Accurate forecasting requires good calibration and reliable input data. It's important to model both expected case and worst-case friction factors, since real-world conditions rarely match the ideal. We must understand the difference between multi-depth models and snapshot data. Snapshot calculations give a quick view of loads, while multi-depth models simulate the entire wellbore. Both are valuable in planning. Friction factors are variable. They change depending on the hole condition, whether it is cased or open, and the specific operation being performed, such as running in hole, pulling out, rotating, or running casing. Buckling is often poorly understood and underestimated. Without proper modelling, drill pipe or casing may reach critical loads, resulting in sinusoidal or helical buckling that impairs tool movement and increases wear. Effective management of torque, drag and buckling requires robust design, real-time monitoring, and proactive operational practices. Next, we'll look at wellbore instability, another risk that becomes more pronounced in high-angle ERD wells. Wellbore instability is a persistent risk in extended reach wells, and it is often time sensitive. The longer a formation is exposed, the greater the chance of failure. Many ERD wells fail not because of operational mistakes, but by design constraints such as casing setting depth or ECD limits that leave unstable formations exposed for too long. High-angle wells typically require mud weight for stability, but this can conflict with fracture gradients or ECD windows. The balance is more delicate than in vertical wells. Operators must also prepare for unconventional instability modes. For example, fatigue damage, hydraulic hammer effects, and self-induced vibrations can destabilize the borehole, even when mud weight is correct. Best practices include proactive mud system design, careful monitoring of cavings and torque drag, and minimizing exposure time through efficient operations. The first part of the BHA and drill string design emphasizes hole cleaning suitability. In ERD wells, cuttings transport is often the limiting factor, and the BHA must be configured to support efficient cleaning. The number and placement of stabilizers is crucial. Too many, or poorly spaced stabilizers, can restrict flow-by areas and reduce cuttings transport. We must also avoid RPM-limited designs. Ideally, the BHA should operate effectively both on and off bottom, with steerable motors set at minimum bend to balance steerability and efficiency. Equipment longevity is another key issue. Long runs in ERD wells require durable components, and an approach that may necessitate multiple specialized bottom hole assemblies rather than attempting to achieve all objectives with a single assembly. Regarding drill collars and heavyweight drill pipe, lighter designs are generally better. The neutral point is less of a concern at high inclination, so reducing weight helps lower drag. Altogether, the BHA should be tailored for long intervals, cuttings transport, and tool endurance. In this continuation of BHA and drill string design, we consider additional key points. Jar placement must be carefully evaluated, and in some ERD wells, jars may not be used at all due to limited effectiveness at extreme reach. Hole cleaning often drives not only BHA configuration, but also drill string design in larger hole sections. Components must provide sufficient flow by area to prevent cuttings build-up. Bit design should focus on 5 key factors: steerability, durability, stability at formation interfaces, compatibility with rotary steerable systems, and a good flow by area. These matter far more than maximizing rate of penetration. In ERD, a steady, controllable bit is preferable to a fast one that causes vibration or trajectory control issues. Ultimately, ROP is a secondary consideration in ERD. The priority is staying in hole longer, maintaining trajectory control, and ensuring cuttings transport efficiency. The overall drill string must balance lightweight for reduced drag with robustness for long, challenging runs. Having now covered BHA design, we'll move to the final slides to review our objectives and close this module. Let's revisit the objectives we set out at the start of this sub-module and see how we have addressed them. We began by reinforcing the definition of ERD wells, understanding that they are characterized not only by long horizontal displacement, but also by the unique operational challenges they present. Next, we examined equivalent circulating density management. We saw how shallow TVDs combined with long laterals produce high ECDs, leaving narrow margins between pore and fracture pressures. Managing surge, swab, and lost returns becomes critical. We then moved into trajectory profile design, emphasizing that ERD paths are not about the shortest line, but about minimizing risk, accounting for torque, drag, hole cleaning, and unstable formations. We discussed surveying and geological uncertainty, where even small errors become amplified over long displacements, requiring advanced survey techniques and improved practices. We also analysed torque, drag, and buckling, and the need for realistic modelling and operational controls. Finally, we covered BHA and drill string design, showing how hole cleaning, tool durability, and stability matter more than maximising penetration rates. Together, these topics give you a comprehensive view of ERD well design considerations. Let's conclude the session. This concludes Sub-Module 2 on extended reach drilling. Please proceed to the short quiz to test your understanding of the material. Thank you for your attention and engagement throughout this session, and I look forward to continuing with you in the next and final sub-module.